Hello, math friends. This is AP Calculus section 6.4 notes. Today we are going to talk about the average value of a function. And this should be pretty intuitive because we know how to find the average of a group of numbers. For example, if you want to find the average of a group of scores on a test, you add all your scores together and you divide by how many there are. We've been finding averages for years in math classes. But what do we want to find the average of an infinite number of values within an interval, right? And again, when we're taking something to infinity, we're thinking about a limit, right? So let's say that we're trying to find the average value of a function f of x over the interval a to b. And again, a to b is that distance along the x-axis. So if we divide our interval along the x-axis into n subintervals, then our delta x would be b minus a, that window along the x-axis, right? That's our distance, divided by n, the number of subintervals. Then our average value would be all of our y values added together. So f of x sub I plus, f of x sub whatever, all the way up to f of x sub n, divided by n, the number of subintervals. Since our delta x is b minus a divided by n, a little bit of algebraic manipulation. If we rearrange that, then it becomes n equals b minus a divided by delta x. And our average value then becomes all of our heights or all of our y values added together divided by that fraction b minus a over delta x. If you keep switch flip that, you've got your 1 over b minus a, and then you take the delta x times each of your y values. Well, that becomes 1 over b minus a, I'm right here, times our sum from I equals 1 to n of all of our y values times our delta x. And then as we increase the value of n, we're computing the average value of a large number of very closely spaced values. So in other words, we're taking a limit. And we know that this, to us, becomes an integral. So the limit, as n approaches infinity, of 1 over b minus a times the sum from I equals 1 to n of f of x sub I times delta x, we write as 1 over b minus a times the integral from a to b of f of x dx. And that is the average value of a function as far as we are concerned. So that is our formula. Really very easy to use because we should know a and b. We should know our interval along the x-axis. F of x is just our function, and we're going to take the integral of it. So we'll be using our rules of integration. So let's take a look at our first example. It says find the average value of f on the given interval. F of x is equal to 4x minus x squared, and our given interval on the x-axis is from 0 to 4. So I know that my f average is going to be equal to, I'm just going to write my formula down first, 1 over b minus a times the integral from a to b of my function f of x dx. Okay, well in this case, my a value is 0 and my b value is 4. And my function is 4x minus x squared. So I'm just going to plug everything in. So for this problem, it's going to be 1 over 4 minus 0 times the integral from 0 to 4 of 4x minus x squared dx. And my function is just a polynomial, so that's easy enough to do the integral of. 1 over 4 minus 0 is just 1/4, right? And then when I integrate 4x, remember I have to raise my exponent, but then I have to divide. So the x will become x squared, and when I divide 4 by the 2, I end up with 2x squared for my first term. And then my x squared becomes negative 1/3 x cubed. Okay, so there's my integral, and I'm evaluating that on the interval from 0 to 4. So now I just go ahead and use the fundamental theorem of calculus, plug in 4, plug in 0, subtract. So I'm going to get 1/4 times 2 times 4 squared minus 1/3 times 4 cubed minus 1/4 times 2 times 0 squared minus 1/3 times 0 cubed. Well, that's all going to go to 0, so we don't need to worry about that. So we end up with 1/4 times 4 squared is 16 times 2 is 32. So 32. 4 cubed is 64, which is not divisible by 3. So I'm going to write that as 64/3. Okay. And then when I distribute my 1/4, 32 divided by 4 is 8. And 64 divided by 4 is 16. So I end up with 8 minus 16/3, which if I would turn both of those into thirds and subtract, I end up with an answer of 8/3. All right, the second part of the notes here is talking about, is there some number C, right? C can be any value that lives between A and B, such that the value of our function f is exactly equal to the average value of the function. And hopefully in your mind, you're picturing, our function and some point that lies on the curve that's exactly equal to the average height of the function. And if you look at the picture there, the answer is yes, right? And this is actually called the mean value theorem for integrals. If f is continuous on some interval ab, then there has to exist some number c that lives in our interval a to b, such that f of c, the value of the function when you plug c in, is equal to our f average, or our f, our value that we calculate. And if you look at the picture here, you can kind of see, yeah, that makes sense, that there should be some value c. And if we just do a little bit of rearranging, if I take that right here, if I take this equation right here, and I just do a little bit of a manipulation, I multiply both sides of the equal sign by the b minus a, then I end up with this new equation right here, that the integral from a to b of f of x dx is equal to our f of c, right, our average value of our function, times b minus a. And that can be a useful equation to use as well. Last example in this section of notes says, given f of x is equal to x minus 3 squared, and we've got the interval from 2 to 5, find the average value of f on the given interval. So we're going to just do another example of finding our average value. So I know my f average is going to be equal to 1 over b minus a, so in this case 1 over 5 minus 2, times the integral from a to b, so integral from 2 to 5 of my function x minus 3 quantity squared dx. Okay, and now I just have to do the math here. Well, I don't have to do a u substitution because the function inside the parentheses is x minus 3, and the derivative of x minus 3 is just 1, right? The derivative of 3 is 0, the derivative of x is 1. So I don't have to do a u substitution, which is nice. So this is going to be equal to 1/3 times, and then when I integrate x minus 3 squared, that's going to become 1/3 times x minus 3 cubed. And I have to evaluate this on the integral from, on the interval from 2 to 5. So now I just do the math here. So let's see, when I multiply 1/3 times 1/3, I have 1/9. And then 5 minus 3 cubed minus 1/9 cubed, right? Just plugging in my limits of integration. 5 minus 3 is 2. 2 cubed is 8. And 8 times 1/9 is 8/9. 2 minus 3 is -1. -1 cubed is -1. -1 times -1/9 is going to make +1/9. 8/9 plus 1/9 is 9/9, which is 1. All right, so that tells me that the average value f on this given interval, the average value of the function is 1. And we're going to take a look at that in a moment. We're going to take a look at a picture of that and see what that looks like, and then you'll actually be able to visually see that that makes perfect sense for this problem. But let's do part B first. Part B says, find a value c such that f average is equal to f of c. So really what this is saying is, right, find c such that f of c equals 1, because we now know that our f average is 1. So we're going to start with f of c would be equal to what I would get if I plugged c in for the variable in the function. So that would be c, minus 3 quantity squared, right? But I know that f of c, I want f of c to equal 1. I want it to equal the average value of the function. So really, I want 1 to equal c minus 3 squared, and I am just going to solve for c. So first thing, if I want to undo a square root, if I want to undo a squared, I'm going to use a square root. So I'm going to square root both sides here. Now be careful. Here's a little bear trap that we could fall into. We want to make sure that we're finding all solutions. So square root of 1 would be both positive and negative 1. And then over here, the square root and the squared cancel, so we just get c minus 3. So when we add 3 to both sides, we are going to get 2 possibilities for c, right? We're going to get c could be equal to positive 1 plus 3, or c could be equal to negative 1 plus 3. So we get c equals 4, or we get c equals 2. So there are actually 2 values that satisfy this for our function. What this means is when we graph it, there are going to be 2 locations on our curve, 2 c values, where the height of the function is the average value of the function. And in this case, we know that the average value of the function is 1. So in our window from 2 to 5, there should be 2 spots where our function has a height of 1. For part C of example number 2, they're asking us to sketch the graph of f and a rectangle whose area is the same as the area under the graph of f. So we're going to start first by sketching what our curve looks like, which is f of x equals x minus 3 squared. So I'm just going to build a coordinate plane here. All right, and we know that f of x equals x minus 3 squared is just a parabola with a horizontal shift 3 units to the right. So we know that our vertex of our graph is going to lie at 3, 0 instead of at 0, 0. And then the shape of the parabola is the same as a normal shape. We don't have any stretches or shrinks or anything. So we would go right 1, up 1, and then we would go left 1, up 1, and we would go right 2, up 4, left 2, up 4, so on and so forth. And so the graph of our function looks like this. All right, now in part A, we found that the average value of our function was y equals 1. So the next thing that I'm going to do is I'm going to add that horizontal line y equals 1 onto my graph, which is this line right here. And as you can see, here are the 2 locations that we found in part B where the average value of our function, which was 1, was equal to the value of our function, right? And that happened at x equals 2 and at x equals 4. And those were the values that we found in part B. And so now part C says, sketch the graph of f and the rectangle whose area is the same as the area under the graph of f. Because remember, the function that we were looking at here was y equals x minus 3 quantity squared, and this was on the interval from 2 to 5, right? So when we think about that, the interval from 2 to 5, here's x equals 5, here's x equals 2. So when we look at the area under our curve from 2 to 5, we're looking at that bit of area right there. But the rectangle that represents the same area as the area under the graph from 2 to f, or excuse me, from 2 to 5, is going to be this rectangle right here, where the base of the rectangle is from x equals 2 to x equals 5, and the height of the rectangle is 1. Okay, so let's write this down. The base of the rectangle is the length of the interval. And the height of the rectangle is our f average, which was equal to 1. So basically what we're saying here is that this rectangle that we've created here is equal to, in area, the area of our function that lies under the curve and above the x-axis. Right, so we have basically this area right here is equal to the area of that rectangle right there, based on our picture.